Hi, Chris Iannello again with part 3 of the PSpice circuit simulation overview, and now on to using PSpice and the Probe Viewer. So in part 3 we'll do our guided tour now of PSpice and Probe. We'll go through the simulation profile settings once more and look a lot closer at a number of them. We'll talk about time domain transient sims, do that on the circuit that we created last time in part 2. Go through adding plots, manipulating cursors, just all the different visualizations of the data that we can squeeze into a few minutes. Talk about how we get that data out to other applications and how to make it look good. And then we'll switch over to AC sweep and bias point solutions. And I have a number of simulations queued up that we can go through quickly. I won't go through the trouble of drawing them as we did that in the last part. Okay. And then we'll, towards the end of this, we'll get into convergence tips and tricks, which is definitely something that you need to get familiar with if you're going to use an analog simulator of this type. So here's the circuit that we built last time in part 2, and we will now go into simulating it. So I'll switch over to the simulator. Here's our schematic. Again, we go over and we look at the simulation settings. It's set for a time domain transient. We said 10 milliseconds, and we didn't specify the step size. The simulation is called Transient. The configuration files, and of course it has a nominal library, which we need for this. Here's the options. You'll notice Reltol and all the others are at default. We don't have either of these things selected, and auto convergence is not turned on. We'll look at this more on a subsequent slide, but this is something we'll spend a lot of time with when we're working, particularly in closed-loop systems. And in Probe, we said all markers on open schematic. So right now we have one marker on the open schematic. I'm going to take that marker out, and I will go ahead and run the simulation. Up will pop up. We see it's running. It's 50, 60, 70%. Up will pop up a window here. But it doesn't have any data in it because, of course, we had no markers on the previous schematic. Let's talk about our markers. We've got voltage markers. This is the differential voltage marker, current into the node marker, a power dissipation marker, and if you look, there is this marker window under PSpice, which provides you some more advanced markers, which really are mostly useful in the AC analysis end of things. So when we do AC analysis and we want to see magnitude of a signal in dB or phase of a current in degrees, or phase or voltage in degrees for that matter, we'll select that there, but we'll save that for then. Anyway, for right now, let's pick voltage of the output. And of course, as soon as we mark it, it turns green because it's a live simulation, and here's our data. And again, that terrible overshoot because we're running that boost converter, the buck converter open loop. So if I want to look at cursors, of course I can toggle my cursors here and I see the values. I can get the maximums, the cursor peak. This is the local min, local max, the slope, and these sorts of things by these buttons across the top here. Now I have the left mouse button held down and I can bring up one cursor. If I want to bring up another cursor, I hold the right mouse button down. And that's how this works. If we want to add now a plot, I'll go plot, add a plot to the window, and let's turn our cursors off for a second. And let's select by clicking on the top plot. Go back to the trace window and let's do inductor current here. And that's going to be green. It's the default color that we initially put in. And so here's our current. And if we zoom in, for example, we can see that the inductor current never actually reaches 0, so that's continuous conduction mode, and it's what we'd expect for the current to look like. And I'll add another plot here. And this time, I think we'll add the differential voltage across the main switch. Zoom into that guy again out here, and of course all the axes are stuck together, so when you zoom in on one, all of them zoom, something that I really wish some other tools would adopt, like MATLAB, for example. And then here's our values. Now, if we want to see where the data points were actually calculated, you can see them here, and it's kind of somewhat jagged, as you can see. Now, let's say I want to come back to this exact point after I rerun the simulation. I go back into my simulation settings, I go over to my probe window, and I say show the last plot. The next thing I'm going to also change is I want to increase the number of points. Now the simulator is going to go through and calculate what it needs to do to come up with the appropriate solution, the iterative solution based on our settings. We can actually minimize the time step. The time step is variable in this solution, but we can minimize that. We can say the time step can be no more than a certain value and cause more data points to be collected. So let's go back at our window, and we see that maybe something on the order of a microsecond would cause this to be a little bit smoother. So if we go in here and we click on our simulation settings and we set our maximum step size to 1 microsecond, apply, OK, and then simulate, we'll get data here again in a minute. Now we're simulating here, and you see that it's a much smoother plot along the bottom, and you also notice that it zoomed right into where we were at before. Very handy feature. Now let's see, this was inductor current. Let's add over the top of that now the diode current. So I'll pick this marker here, current, into this. The second color is always red, and there we have it on the middle plot. I'm going to delete the top plot so that we can see it better. We'll delete the top plot. Oh, excuse me. Delete the plot, and then I'll delete the bottom plot as well. Okay, now we have our diode current and our inductor current on the same plot. When I want to change the thickness of a line, I'll hit Trace Property, and I'll come up here and change the width. And that's particularly useful when we want to be presenting data. Also, if we're not going to show a color plot, we might consider putting a character over the top, a symbol, for example, like a diamond. We'll change our width again, we'll show the symbol, and we'll say OK. Anyway, so this is how you change the look of the traces. Now when I want to cut and paste that into Word, I'll copy that to the clipboard. It'll ask me some options. I always say change white to black, and I let this checkbox be checked. I say OK. And you'll notice that if you paste that into PowerPoint, for example, you'll get different results than if you send it into Word. I recommend you always send your results into Word first, and I'll show you what I mean. When you first paste this into Word, it'll appear like this with basically the system font. If you right-click on it then, click Edit Picture, it comes much clearer when you basically expand that. So that's the way that I always take my graphics over to presentation. Okay, so that's everything to do with this particular one. We've probed around on it a little bit. We've added a few traces. And then, of course, when you're over here, you can do math, too. I can say ID1. I could say I of L1, current in L1, minus I of D1. I can delete this one, and you now know by this is, of course, the switch current. Now, I did that with an expression. If I put the switch current on this plot, and go back and look, it's an exact overlap. So, this is our initial simulation. Now let's switch over, let's change gears to another simulation. This kind of focuses on the closed loop example. If you recall, if we go back to the example that we just had and we look at strictly the output voltage, I'll take all these markers off, I'll look at the output voltage here, I'll right click, say End Mode, and I'll go full screen, zoom fit. There is our data, our output voltage. It overshoots tremendously. And of course it does settle in on desired operating point at 24 volts after a lot of ring, milliseconds and milliseconds of ring. Now, a continuous conduction mode buck converter, which is what we're simulating, the duty ratio, the output voltage is strictly a function of the duty ratio. When the inductor current actually reaches 0 in discontinuous conduction mode, when the load's light, the output voltage is really a function of the load and other factors. But in CCM, in continuous conduction, you don't have that. So you do get to your nominal 24 volts, but it's painful. It overshoots tremendously, and if there was a transient here, you'd see a terrible ring. Let's investigate closed-loop control because although it's predominantly a power electronics subject, it'll be a good example for how we deal with convergence. Okay, let's close out of all of this. And let's go to our next schematic. So now what you see here is a buck converter, and instead of a diode, a D-break there, you have an ideal, basically it's idealizing a synchronous rectifier. You have a switch connected like a diode so that when the voltage is forward this way it conducts, but it blocks going the other way. And you also notice that the on-state resistance, I'll zoom in here, the on-state resistance of this switch is set very low. Now you'll also notice that there's this capacitor, a 10 nanofarad capacitor, C snub 1 across here. And I'd like to talk a little bit about what that is. Sometimes when voltages, particularly across switches or across discontinuities, change abruptly, it drives the time step on the simulator such small values that it'll cause a convergence failure. It's working too hard to manage it. So a way to solve that problem, particularly when you see that during a convergence failure that the voltages at a node were extremely small or very large, actually just extremes in general, a way to do that is to put a capacitor across those 2 points, across those nodes, to try to slow that change somewhat. So that's what these numbers are for. It's a means to manage convergence. So let me zoom back out. And up here, this is one circuit, an open loop buck. If we look up here to the upper right, there's another circuit on the same page. It's the same buck converter, but now instead of a V-pulse source driving our gate, we have this network here. This network here represents basically a regular op-amp compensator circuit. It's a type 3, I believe, and then a pulse width modulator with duty ratio limit control. This effectively, minus the R's and the C's here, is your typical PWM control IC. So we were implementing it in blocks so that's more easily seen. I think there's a couple subsequent examples where I actually used the integrated circuit part from Unitrode, but it's easier to see what's going on here, and we're closing the loop on the buck. You see that there's a load transient at 9 milliseconds where we reduce the load from 6 ohms to 3 ohms, and we're going to simulate this and compare the open loop to the closed loop response. See, it's simulating very quickly, and see we have our comparison. You'll notice that the open loop in red does what we expected to do. It goes way high. Now notice the voltages are a little different on this schematic, but it's still the same principle. The voltage goes way high on the open loop buck, rings for a very long time, and then steadies out. When there is a transient at the 9 milliseconds, when the load is effectively stepped by 100%, you go from 6 ohms to 3 ohms, you have a long ring, but in the closed loop system, it's nice and smooth start because of our soft start circuit that's associated with our PWM IC, and then we see the very minor transient due to the closed loop control. Now, I want to point out a couple things back here. You'll notice that in the simulation settings for this, I've turned the auto convergence on. If I turn that auto convergence off and I come back here and I say OK and I go to simulate it, there may be, it'll be hit or miss on a closed loop circuit like this. And we actually failed. We failed to converge. Now I can try to run it again, and just to demonstrate what it does, I'll restart the simulation. It tries, but it immediately fails. Now, generally speaking, the way that I would handle something like this, is I would put a snubber cap across things that I know are troublesome for the simulator, like switches that are nearly ideal that are turning on and off. And this shouldn't make you think that you don't have convergence problems with non-ideal components in your simulation. You have it no matter what. But this was an easy way to point out how the problem happens. Sometimes there are actual physical issues where you have an unstable control loop, and the convergence issue is actually a result of the physical phenomenon. But in this case, it's generally just the abrupt changes. Now, when I put that 10 nanofarad back in there, let's say cancel. Let's come back over to here, 10 nanofarad, and let's restart the sim. And now it seems to like that. And you see problem solved. We should get our same results back, which we do. Okay, so that's one method to do it, and this is the way a lot of us used to operate. We would either slow nodes of the circuit down or differentially apply capacitance between 2 points to try to slow the rate of change down. Another very common practice in the options file was to take rel tol to 0.01. Now you notice it was the default originally, but the auto-converge routine, I think, made some adjustments on it. The other option is to turn autoconvergence on, and that's something else I wanted to show you. I can take this guy out. Let's take it back out and actually run it without autoconvergence just to confirm that the simulation fails to converge. And we have our fail to converge. I can push it again just to make double sure. Restart the simulation. And of course it fails to converge again. But I can go in here and click auto convergence and do OK. Let's cancel that and rerun it again from the button inside of PSpice. Click restart. And it simulates. So this is the kind of thing that it's doing, and what it does is it does that manual tuning that you would have done manually yourself. It goes through and alters iteratively these values until it gets a functioning solution. Anyway, a brief introduction to autoconvergence and the kinds of things you can do. The most effective thing you can do when it comes to improving convergence, especially in power electronic circuits, are the virtual snubbers that I just described by putting caps across these points or to ground, or adjusting rel tol from the default value of 0.001 to 0.01. Okay, so that's basically autoconvergence in this control system, and it's interesting to note how fantastic the closed loop control improves the response. Next, let's move on. Actually, let's go back to the PSpice charts, the PowerPoint charts, and talk about the normal SPICE calculation flow. Now, generally there's nonlinear circuits involved, just like this power electronic circuit. There's large signal time domain analyses, and then there's small signal frequency domain analyses. And these are both preceded by a quiescent bias point calculation. And I can show you that in the AC analysis next. Now, the important thing about AC analysis is it requires a linear circuit. Now, looking at what we have here, you can see that this switch changes state, so we basically have switched modes here. We have a circuit mode where when the switch is closed, you effectively, when this switch is closed rather, you have energy transferring all the way through the load. And then you have this other mode that when the switch is open, energy and currents freewheeling through the load, through this freewheeling diode, through the inductor. So basically you have two totally separate circuits that change as a result of these two switching elements changing state. You can't do a linearization directly of a circuit like this. There are a number of simulation packages out here that create average models from this, basically by time averaging the amount of time that you're in mode 1 versus the amount of time that you're in mode 2 of this circuit. but PSpice is not one of those. So you have to have an average model to be able to run an AC circuit analysis, an AC sweep, to get some frequency response here. So let me take you to that example. What I have here is an average model. It's a model actually generated based on a paper that was authored by Dr. Vaporian, who is at JPL now and has been for a number of years supporting NASA programs. But this is a model that's in the PSpice libraries of his creation. And when you go through this this circuit now, since it's an average, there's basically nonlinear algebraic equations in there. When I run an AC sweep analysis on that, I will show you the simulation settings there. We'll do an AC sweep, we'll do logarithmic, we'll start at 1 hertz, go up to 100 kilohertz, do 101 points per decade. You're going to find that this is a very fast simulation, and you never have a problem with the AC sweep once the bias point solution is solved. When I go and I do the simulation there, we basically have dB, see the dB marker is the advanced marker here, in green as the V of output, and red is of the loop gain. And let's go back and look at those magnitudes. We have, here's the output, basically, and let me show you where we're providing our inputs at. The sweep input here uses a part called vSource, and it has a DC attribute and an AC attribute. The AC attribute doesn't come into play when we run transient analysis or time domain analysis. It's a special attribute of the source that's only valid when we're doing an AC sweep. So what we've effectively done here on both of these guys is we've applied a 1 volt AC source that is what we're going to sweep frequency on, and then we're going to measure output based on wherever we put these markers, VDB and VP, VDB and VP. And you'll notice that they didn't light up here, and sometimes that happens with the simulator. The color of the trace and probe doesn't match the color of the marker in the simulation. Sometimes that breaks. That's what's happened here. But what's important to note is this is the way that one closes the loop on a power converter. An average model, which provides a transfer function, a Bode plot of the main power stage, so that we can apply the classic linear control techniques that engineers know and use so well. In this case, we basically put our compensator up on the screen. We look at what our transfer function is from control to output, from the sweep output to output, and then we look from output to loop gain, and we're able to put those sorts of things up on the screen. You can see that the red here is the compensated loop gain. When we talk DC to DC converter control, I'll explain how this is a more desirable transfer function, and the gain and phase margins are both stable on this converter. So that's the AC sweep in brief. If you have any additional questions about this brief overview to PSpice, the transient and the AC sweep simulations, please don't hesitate to shoot me a note. Thank you for your time.